Okay, so the next speaker will be Fernando Galaz Prieto from Tampere University. We will talk about a Zephyro interface that is a multi-channel transcranial electrical stimulation interface. So please go on. Thanks.
All right. Well, thank you very much for inviting me for this seminar. And the topic is, like you said, multi-channel transcranial electrical stimulation in Zephyro interface, sparse, optimized, and regularized stimulus. My name is Fernando, and all right. So Zephyro, it's a brain image toolbox, which is designed to provide a multi-model open source platform for finite element modeling based using GPU accelerated forward and inverse computations in MATLAB environment. Here, as you can see in this figure, you see the workflow, excuse me, of how Zephyro process this information in three short phases: a segmentation tool, mesh tools, and provided inverse tools. Okay, but I'm not going to explain how Zephyro works here. I'm just going to provide you the results of what I did last year. So before I further continue with the equations that I have to present, I have to explain the forward modeling and the inverse modeling that was carried on for this project. So first of all, the forward modeling is known as the calculation of electric and magnetic field patterns over a given geometrical model. The inverse problem is a calculation of the time-dependent and position values over the already measured field pattern. Now, here, what we see in the screen is the partial differential equations for omega, and omega in this context is the head model where we're going to simulate the calculations of these electrical fields, the resistivity.
Fernando, sorry, is there a gray line on the right?
Oh, yes. I apologize. I didn't saw that. There you go.
Okay.
Okay,
Thanks
everything
a
correct?
lot. Yes,
Okay.
sorry. Thanks.
I'm so sorry. Okay, moving on. Okay, first we see the partial differential equation, and the simplified version here is the simplified form that governs the partial differential equations of the electrical potential in the head omega. Now, the point electrode model and the complete electrode model are two electrode modelings that are essential for the reconstructions. The point electrode model, which is the current standard for EEG, assumes that every electrode in the head is a neutral passive point in the domain, while in the complete electrode model, it takes into account the electrode shapes, the contact impedance, and the shunting effects. For this reason, it is important to take into account the alterations of the underlying electrodes, excuse me, and the underlying electric potentials to the current circulations on the contact surface. Now, as we move forward, and in the case of multi-channel TES, the simulated electrodes are the only relevant current sources, which in this context, the resulting primary current density will point to 0. This is why we have the result here in the simplified form 0. Now, in order to find the appropriate model for solving such equations, the head model is simulated through a montage of L electrodes, and we denote the current applied on the L electrode by IL, as well as their potentials UL and the impedance ZL. And here we have, in the bottom, we have the three boundary conditions in a nutshell. Here you see that the first condition states that there is no current that's flowing in or outside from the head model, other than the ones that we define, that we are going to calculate. The second boundary condition states that the total current flux in that L electrode is equal to IL. And the third boundary condition states what is the relationship between the electrode, the electrodes, the potential electrode ungrounded, and the potential underneath the electrode. Moving forward, in order to calculate the current pattern in the head model, we are required for calculating a resistivity matrix, as you can see here in the first sentence, where z is lowercase z is a coordinate vector of the discretized potential, use the ungrounded electric voltage, and y is the injected current pattern. Moving forward, here we also need to obtain the volume current matrix, yes, defined as F, which evaluate the Cartesian components of the volume current density when multiplied by the coordinate vector z of the discretized electrical potential distribution U. The entries of this matrix are given here. Well, we then define our lead field matrix of MCTS as follows, which is, you can see here in bottom, as it is L. Now, the optimization procedure, the main question is, what am I trying to optimize here? What is the main scope here? Is that subjects that had underwent to brain stimulation sessions have reported sensations of skin irritations where electrode has been attached to. As a response, I carry out an investigation for a method that can help us understand how to reduce this uncomfortable characteristic by analyzing the possibility to reduce or mitigate the total amount of potential emanating from the electrodes. Thus, finding a way to reduce the global maximum and minimum level of current required for this stimulation test. This reduction can be approached through L1 regularizations, which is a method that is used for finding unique solutions to ill-posed problems. And we concentrate the following minimization problem as it is followed. Here you can see we're trying to minimize the L1 value of the L time y minus x plus a regularization parameter. This regularization parameter is the penalizing term that will give us the required values to promote the sparsicity that are located in the promote the sparsicity of the current injected in the head model. This was done by using the linear programming and using the dual simplex methods. Here, the linear programming problem consists of a problem of maximizing or minimizing a linear function. In this context, the problem is to find the optimal regularization parameter, alpha, which can minimize the y current distribution over the electrodes by the equations that you see here in the screen. In this case, the G, Y lower, Y upper, X, and 1 transpose are vectors as G as matrix. The Y lower and Y upper are considered as the lower bound and the upper bound of Y, respectively. Now, here in Zephyro, well, this is a screenshot of the Zephyro. Here, during my studies, I conducted this experiment on these three highlighted sections: the placentral gyrus in red, the occipital lobe in blue, and the superior temporal gyrus in cyan. Now, this is a slide from, I think it was for my master thesis seminar. In this, as you can see in the figure here, you can see the electrical field distribution over the Y matter when the synthetic source is simulated at the visual cortex. Again, the image was generated with using Zephyro interface. Here, with Zephyro, I estimate the electrical field distribution provided by the users. We add the constraints of the problems. We apply the L1 parameter regularization to promote sparsicity, and the outcome will be the reduction of intersubjective variability. Now, some of the results that we can see here, on the left, we see the current values. In the middle, we see the residual values. On the right, we see the maximum absolute sum of current values and residual. Note, the minimal cost highlighted as a green dot. Here, by the way, these results are from the occipital lobe, the blue one on the back of the head, left hemisphere, by the way. Okay, and here we have a comparison of the non-regularized versus an optimized regularized current pattern, distributed across a total of 128 channels using the synthetic source as the placental. Oh, my bad. This is the placental sulcus. I apologize. Anyways, what we can see in the bar plot, the gray bars are the non-regularized results, and the black one is the regularized results based on the combination of optimal tolerance and the regularization parameter that yields the lowest amount of total current obtained in that given area. Here we have, as an extra function here in Zephyro, I also conducted a thresholding results using the same methodology, the dual simplex, but in this context, I apply a 10% filtering threshold, in which some of the electrodes that do not yield more than 10% of the results will be reduced to 0. And once again, the calculation is redone with the same threshold, the same tolerance and the same parameter on that given time. Here you can see that a non-threshold version will have a total of number of non-zeros 53 out of 128, while a thresholded aspect will reduce these values to 74 out of 128. Right out of the bat, we can conclude that using just a threshold will filter out some currents, actually some electrodes that we don't really care too much. So for that reason, the potential that is supposed to be on that electrode is going to be redistributed in another electrode that actually has plays a bigger role in transcranial electrical stimulation. And here also in Zephyro, we can also perform that reconstruction. As you can see here, once again, maybe it's not very easy to see, but you can see there is like a green dot in the post-central sulcus, left hemisphere. And carry on with these results, we see the general results, which the general results means a non-regularized version. Then we see a threshold version, and then we see a regularized version of said result. Once again, the tomography as presented here, same characteristics, general, threshold, and active. And moving on to the current edition of Zephyro is the next steps. This is what I'm doing on the office right now. I am conducting some test limitations where instead of using a fixed value of how much amperage are we allowed to use in the transcranial direct current stimulation, for example, which is from 0.5 to 2 milliamperes. How about if we conduct infinite to minus infinite, or we get out a little bit of the recommended dose? So instead of 2 milliamperes, we can use 4 milliamperes, which, by the way, there are some studies that actually conducted 4 milliamperes, although the itchy sensation, of course, is more present in these studies. Another next steps that I'm performing right now is the estimation of parameters that deliver the lowest value possible based on the boundaries that are constructed by the user. And also the next step will be build a decision tree, and eventually that will lead to an artificial neural network where we can integrate the results obtained based on the position of the source. It can be the limitations of the test, the range of how many electrodes are allowed to be used, because in these studies we use 128 electrodes, and the team is thinking about how about if we start doing simulation of other other head models that contains a smaller range of electrode voltage. The objective where this is going is to include a simulation of a 4x1 high definition transcranial direct current simulations in which the Zephyro interface will be able to determine where exactly should we allocate this 4x1 TDCS electrode setup based on either the source position, the orientation, the direction, and the amplitude of, say, source that we simulate in this context. And for me, I think that's enough. Yes. And well, thank you very much. And this was the case of multi-channel TES in Zephyro interface, sparse optimized, and regular SS stimulus.
Okay, thanks a lot, Fernando. Very interesting. So we see if is there some question. Okay, Sarah.
Hi, Fernando. Thank you very much for this very nice talk.
Thank you.
I have a quite technical question. I may have not completely understood what you were doing, but can you go back to the figure where you were using a threshold method to select some channels?
I guess this one?
No, the one in which you were compared I think it's two later. Okay, this one.
Yes.
I have actually two questions. The first one is a more philosophical one.
Yeah.
Why you are actually selected channels? I mean, if I understood correctly, here you are solving the forward problem, right? So you have a source and you look at which is the activity in the channels. But then why you put the threshold on the channel and you redistribute the activity? And the second question, again, it may be I didn't completely understood the methods. If I look at the figure, I see that there are channels with an higher activity. For example, I see on the left side of the figure that there are two channels with a very close activity around 0.05. But then I see that only one of them remains, while there are channels with much lower activity that remain. So it seems that there, I mean, how this threshold actually work, it seems that you don't select the channel with the highest activity, but you do something more, right?
Yes. For the first question, why the thresholding aspect? Okay. As an experiment, I performed this calculation of the tolerance optimization and the regularized parameters, which yield a setup of the 128 electrodes. Then I conducted a threshold across the all 128 electrodes. The main reason is because since we are trying to promote sparsicity based on the L1 norm and using the dual simplex method, some of the electrodes, if they're not thresholded in this aspect, if I redo a calculation here, eliminating the possibilities of obtaining some noise or some instance of any other perturbation that the clinicians may add, the threshold aspect serves, philosophically speaking, as tolerance for the clinician or the patients or any other anomalies that are not presented in this calculation. Now, for the second questions, you do say about, I think you can see my cursor, right?
Yeah, exactly.
Okay. Yeah, you mean about this combo, right?
Yeah.
These two guys. Okay. The selected threshold randomly, it was just a simple test here. This was a 10% opportunity here. Some of these electrodes that do not yield more than 10%, they were mitigated, but the same calculation was done now based on the number of active electrodes that survive after the threshold. So what you see here on the right side it's not literally a filtering. It's not just removing the 10% per se. It's the reduction of the current calculated values, then recalculate using the same tolerance, optimized tolerance, and the regularization parameters based on a now threshold active electrodes of the former case. And here we see that indeed some of activity of the in each electrode, some fluctuated a little bit higher, a little bit lower. Some of them do preserve almost the same value that you see here. For instance, indeed, the tiny one here, let's just call it the right from the pair, did mutate. But as you can see, there is more positive activity than in the right side. I apologize, this picture might not be the biggest one itself, but take into account, for example, you see the obvious range here, that there are some electrodes that do present very high activity, and here we do not see it. Yet the peaks, the local and global maximas that we obtain here from these electrodes are higher in this context. This is because it is concentrating the electrodes that is missing here. So the whole idea of this project is to not have
that maybe the one that is missing is close to the other one, but you have lose this spatial information because they are like on.
Oh wait, actually yes, you're right. It's actually the left one, not the right one. I apologize. It is true.
Okay. But
this is only a 10% threshold, which is naturally, it's just a dramatic representation. Naturally, I do not add the threshold, but this just in the context of, for presentation purposes, I just want to see if, what will happen if I threshold it? Oh, I can see that it gets more dramatically. It's higher peaks, lower peaks, but I have less number of electrodes that I need to have them active during the session itself. This is what this is the main scope of the project, is how to reduce the number of channels that I need to have available. Because in the terms of the 4x1, you see that you only have 1 positive and 4 negative, or vice versa. And this is where I am going to. I don't want to have all the channels available at the same time, because in the end, some of them might not be necessary to have. Or if I can change the concentration of activity in areas that I know that might not be fruitful, how about if I just put it in electrodes that are actually doing the real test here? It's like provide more resources to the channels that are important and remove the ones that I don't need and I don't care. And this is the reason why the regularization and maybe threshold can be even more useful than just using the regularization itself.
And sorry, Fernando, since you told about regularization, how did you choose the parameter in L1 approach?
The values that I choose, honestly speaking, I just choose from a range from, it can vary from a regularization parameter of plus minus 0 to, it can go to 1 power 15. And To be honest, I just put this in MATLAB and I just see, and I hope.
Okay. Did you adopt an empirical approach, to choose?
Honestly, yes. I did an empirical approach during my initial studies, and now that I actually got a nice guesstimate. All right, now how about if I do a lattice approach? How about if I start using L2 normalization? Or how about if I start extracting features out of this? And this is the next step of what I do in this. I am surprised.
It was my next question. What are your next steps? Okay. So also to adopt other inverse algorithm, no?
Excuse me, what was the question?
What are your next steps for the interface? Also, do you want to try to use different inverse methods?
Well, technically, I am making this entire exercise in a fancier way, and I'm trying to accommodate these resources in the Sephiroth as a plugin, so you guys can download it and can be able to manipulate with the same parameters, or maybe you can come up with your own variables if you wish to. And the whole scheme of this project is that my personal goal is to, or personal vendetta is that I actually want to include a neuronal network, artificial neural network, for determining which parameters are actually usable, because based on which parameters you select and based on the tolerance that you select, the electro channels are distributed in a different way, in a different behavior. And of course, if changing from one tolerance from another in terms of power 10, or maybe just like in decimal or even power -3, it can change the complete dynamic of how the electric channels will look. Although the potential will be almost the same, and by almost the same, I mean like it can fluctuate between 0.001 milliamperes, but still the electro channels will behave completely different. And I don't want to have a result analysis that give me, okay, you only need to have 3 channels, and suddenly the next permutation will give me 27 channels. So something is off there. So I have to start analyzing some features here. All right, how many channels are available, which is appropriate, which is not appropriate. But of course, if you think about the number of channels, the number of parameters, the number of tolerances, the geometry of the synthetic source, you will end up have almost infinite number of opportunities. And yeah, you know where this is going.
Okay, perfect. Okay, thanks a lot again.
Thank you very much. Is there anything else?